This part of Chapter 7 will focus on the two major substitution type reactions, SN1 and SN2. Beginning with the SN2 mechanism, you can see that it occurs all in one step, which means the carbon-bromine bond breaks at the same time that the negative charge on the oxygen nucleophile is donating electrons to the partially positive carbon. The S stands for substitution, the N is nucleophilic, and the 2 is for second order. SN2 reactions have second order kinetics. This means that the reaction is bimolecular, in that both the alkyl halide and the nucleophile affect the rate. The rate equation for the example reaction from the last slide would be rate equals rate constant K times the concentration of CH3Br times the concentration of CH3CO2 minus. A general energy diagram for SN2 reactions will have one hill because there is one step. Note that the 2 in SN2 means second order and not the number of steps. Energy is on the y-axis and the reaction path going from reactants to products is on the x-axis. Here is the starting materials, then an increase in energy to form the transition state, and once again a lowering in energy to form the products. The energy difference between the reactants and the transition state is called the activation energy, and the energy difference between the products and the reactants is the enthalpy of reaction, estimated from bond dissociation energies. The next concept to examine is the stereochemistry of these reactions. There are two ways for the nucleophile to approach the substrate. The substrate is the alkyl halide. The nucleophile can approach from the front or from the back. The front side is defined as the same side as the leaving group, as shown in the first picture. The back side is defined as the opposite side of the leaving group. You may have noticed that the approach of the nucleophile will give two different products, which are enantiomers of one another. There is a preference for SN2 reactions, and it is for the nucleophile to approach from the opposite side of the leaving group, called the back side. I want you to notice that when the nucleophile approaches from the back side, the product with the nucleophile attached will have an inversion of stereochemistry. An inversion is a swapping of one stereochemistry to the other. For example, an S starting material would invert into an R product. An R starting material would invert into an S product. A cis into a trans, and a trans into a cis. The reason for the backside approach of the nucleophile can be seen by further examining the transition state. Transition state shown here. The mechanism is showing the approach of the nucleophile to the side opposite of the leaving group. This would be called the backside. In the transition state, notice how the nucleophile and leaving group are on opposite sides. Think about the size of a halogen versus the size of something like a hydrogen. It is much easier for the nucleophile to reach its target from the less hindered side of the molecule. Studies using a label have proven this approach. An example label uses deuterium in place of one of the hydrogens. Deuterium is an isotope of hydrogen and can be differentiated in instrumental studies. The leaving group breaks away from the molecule as the nucleophile is attaching to the electrophilic carbon. This one-step process allows for carbon to never have more than an octet of electrons. See the product and how the groups are inverted. The D, R, and H have flip-flopped like an umbrella turning inside out. The stereochemistry will swap. Here are two example reactions showing the complete SN2 mechanism. When asked to draw a mechanism, remember to show the curved arrows. The mechanistic arrows are shown in red on this slide. The nucleophile is the negative or partially negative molecule, and the electrophile is the positive or partially positive molecule. Both of these examples use a negatively charged nucleophile and a partially positive carbon electrophile. For practice, draw out the mechanism for each, as it is shown here. Also, write out the stereochemistry of the starting material as R or S, and then do the same for the products. There is a difference in reactivity depending on the classification of alkyl halide, which is also called the substrate. As stated here, as the number of R groups on the carbon with the leaving group increases, the rate of an SN2 decreases. The less substituted, the better. So, if the leaving group is attached to a carbon with 3 hydrogens, which would be called a methyl group, then the rate would be fastest. The classifications are shown here. The primary has 1 carbon group attached. The secondary has 2 carbon groups attached. The tertiary has 3 carbon groups attached. Notice that the number of hydrogens attached to the electrophilic carbon decreases by 1 each time a new carbon group is added. Trends that have been found are that methyl and primary type alkyl halides are best suited for an SN2 mechanism. Secondary alkyl halides are slower, and tertiary alkyl halides do not undergo SN2 reactions. The reason, as stated here, is due to steric hindrance effects. R groups are larger than hydrogens, and there is not enough room for the nucleophile to approach a tertiary substrate. Electrostatic maps are showing the differences in steric hindrance effects. Remember, the nucleophile needs to approach from the backside, which is the side opposite to the leaving group. The less steric hindrance, the easier the approach. The best case scenario is for 3 hydrogen attachments to the carbon with the leaving group, is shown here. The next in line would be 1 R group and 2 hydrogens, as shown in the primary alkyl halide example. The secondary type here, with 2 R groups, 1 hydrogen, is still possible, but the rate is slowed down. The nucleophile will try to fit over the hydrogen, right there, and there is just 1 hydrogen attached this time. The tertiary is pretty much impossible because the approach of the nucleophile to the electrophilic carbon is blocked by 1, 2, 3 attached R groups. To organize everything in your notes and in your minds, let's go through a summary of the characteristics of the SN2 mechanism. The kinetics are second order, which means that the concentrations of both the alkyl halide and the nucleophile affect the overall rate of reaction. The mechanism is one step, where the nucleophile attaches at the same time the leaving group departs. The stereochemistry will be inverted if there is a chiral starting material, or if it is cis or trans, because the nucleophile needs to approach from the less hindered side, which is the back side. You saw on the last slide that the unhindered alkyl halides reacted the fastest. The methyl alkyl halide and primary alkyl halide are best for SN2 reactions. Secondary alkyl halides also react, but their rate is slower. And tertiary alkyl halides are pretty much impossible for an SN2 reaction. While everything is settling in, I want to show you a couple applications. Here you can see the SN2 reaction in the synthesis of drugs. The second structure contains two chlorines, so the carbons next door, here and here, would both be partially positive. The lone pair of electrons on the nitrogen here and here would allow these two to act as good nucleophiles. The lone pairs attach to the carbon and send off the chlorine. It happens 2 times, one for each of the electrophilic carbons, one nucleophiles, lone pairs, the other nucleophiles, lone pairs, to result in this product, a drug with the trade name Myambutol. A second example of SN2 reactions is in the synthesis of Prozac. The SN2 step is shown from here to here. Notice there is a primary alkyl halide in this primary alkyl iodide. We have one R group right here with the rest of this molecule, 2 hydrogens. The lone pair on the nitrogens, it's a partially negative nitrogen here, is the nucleophile, would donate electrons to the partially positive carbon, send off the iodine to get this structure. And then in some other steps, you could add on the other ring here. Now don't memorize these two reactions. They're just to show some real-life usage of the SN2 reaction. Well, that ends this part of the lecture. In the next part, we'll look at the SN1 reaction.